First, I should really thank Urvashi Sinha and Professor Dipankar Home for asking me to talk at this meeting. Very foolishly, I suggested a title of Leggett, Superconductivity and Superfluidity. As I began to wade into the subject, I realized that it was very foolish of me to even think about talking on such a thing, because this is the thing on which Professor Leggett has made foundational contributions for more than half a century. Then I realized that I should change, and I changed to something which is incomplete work, but then I felt that indiscretion among friends is better than foolish valor. So that's that's the origin of this talk. Okay. This is a very incomplete work, inspired by a lot of experiment. Okay. The fact is that all metals, almost all metals, show an intrinsic high temperature electrical resistivity that is linear in temperature. This is a fact. Now, out of these, it seems that a subclass shows very high values of resistivity, which is also linear in temperature. The linear regime extends over a very wide range of temperatures, from very low to very high temperatures, even up to their melting point. The resistivity values are enormous. They exceed what is called the quantum low temperature or Motty of a Reagan limit. They do not seem to show signs of saturation in their electrical resistivity value. Now, this is called, well, and there are very nice words, bad metals, no quasi-particles, etc., etc., which are used to describe the situation. This phenomenon has given rise to a large number of theoretical explanations, theoretical attempts, including the very attractive idea that actually in these metals, these metals are somehow close to Planckian dissipation limit. That is, their relaxation rates are very close to a limit kBT by h slash, which is enforced by quantum mechanics. Now, what I am going to talk about is first, I will present some experimental results, some slides, and then a microscopic theory which is incomplete for the case of strongly correlated metals based on an unpublished, also an unpublished general approach to strong correlations, which was developed in collaboration with Deban and Sa at Banaras University in Varanasi. Now, the pictures I am going to show are all lifted from either a talk by Kivelson in 2011 on metals in which the quasi-particle picture fails, or a PRL paper in 2013 by a number of authors, out of whom I know two, Gaby Cotelier and Antoine George, on how bad metals turn good, or spectroscopic signatures of resilient quasi-particles. Okay, so let me start. You see, copper is something which we all know, and here I show the electrical resistivity of copper as a function of temperature. And in this field, it is important to know numbers and know and perhaps even respect. So here you see the resistivity is rather small. It is a few micron centimeter, 2, 4, 6, and so on. Copper is a very good metal. So its electrical resistivity is very small. But it is not linear at very low temperatures. As a matter of fact, there is a very famous result due to Bloch and Gruneisen, which says that it should be, for very pure metals, it should go as the fifth power of the absolute temperature. But you see that for most of the temperatures accessible to us, it is linear. Okay. Now, there are not so good metals. Examples are these niobium-310 and niobium-3 antimonide. Here you see that the resistivity is sort of linear somewhere, but then it begins to show signs of saturation. Here the resistivities are rather large, much larger than here, 50, 100, 150 micron centimeter. So good metals, resistivity low but linear. bad metals, resistivity has a linear regime, but signs of saturation. Now, then there is the other thing which I would like to introduce, which is what is called the Mott-Yoffe-Regan limit. This comes about simply because electrons are waves. So if electrons are waves being scattered by somebody, then that somebody better be near at hand. In the case of electrons in metals, the minimum distance between scatterers is expected to be the lattice constant in crystalline metals. So if the mean free path for electron collisions is of the order of the lattice spacing, then the thing is, as scattered as it can be. And that sets a limit for the lowest possible conductivity of the system. The other idea which is due to Mott, this is the idea due to Yoffe and Regan. The other idea which is due to Mott is that, electrons are waves and their wavelength is 2 pi by kf. Where kf is the Fermi wave vector, magnitude is the Fermi wave vector, and if that wavelength is of the order of the electron mean free path, so there are many formulations of it. One formulation says it is greater than 1, another formulation says it could be greater than 2 pi, whatever. I mean, of course, 1 and 2 pi are quite different if you are interested in numbers. But all right, this is the idea of Mott, that after all, the mean free path of a wave which is being scattered cannot be shorter than its wavelength. Now, what is the meaning of cannot be is another issue. But these are interesting regimes of crossover in the character of electrical transport in systems. There is a simple kinetic theory kind of description of the conductivity, which actually this should be conductivity, which says that the conductivity, which shows that the conductivity is E square by h times kf by 3 pi times kfl. Now, if kfl becomes of the order of 1, that gives you what is called the minimum metallic conductivity. Many metals actually respect it, and it's an old observation that many disordered thin films, they have a resistivity either less than 30,000 ohms or several megohms. The resistivity has to be either less than 30,000 ohms or it's an insulator. Okay, but fine, let us see what actually happens. Okay, then I'll go to the more primitive approach. Fine. So here I show the resistivity of some metals as a function of temperature. This is lanthanum cuprate. You notice that its resistivity increases linearly without showing any signs of saturation or leveling off. And here is the Mott-Yoffe-Regan limit. It's a band, it's a crossover. It's not a very sharp, precise number, but it is sort of expected to be in this range. So you see that the resistivity increases like that. So it's a very strange thing. By comparison, the resistivity of a very dirty metal, niobium-3 tin, increases linearly and then shows signs of saturation. So I have shown here a number of other examples: TTF, TCNQ, vanadium dioxide, strontium rutherate. In all of these, the electrical resistivity increases linearly and happily crosses the Mott-Yoffe-Regan limit. There is a class of systems in which the resistivity increases linearly with temperature, but if you go to very low temperatures, you find that yes, it goes quadratically with temperature. And that makes many people very happy, because quadratic temperature dependence is what you expect in a dirty Fermi liquid. So it's Fermi liquid, good. So, but then it shows linearity of resistivity at high temperatures. This regime can be small or large. In this particular system, it is, okay. sorry, I have mixed up things. I wanted to say all the things I said about this graph. You see here, you see again that the resistivity increases with temperature, strontium ruthenate. There is a T-square region, and in spite of that, at higher temperatures it does increase. Now the value which it can have can be, as shown here, about a milliohm centimeter, or it can be many milliohm centimeters, as it is in rubidium-3 carbon. That is essentially Buckminster fullerene, in which you put some rubidium. Okay. Now this has been an observation for a long time. This is not new. There has been a lot of effort to understand this. One such effort is a numerical calculation for a whole doped metal in the Hubbard model, which was done by a number of people, including Cotelier and George, using the dynamical mean field theory for treating strong correlations and for a strongly correlated metal. And what they did find was that the resistivity in dimensionless units of the Motty of a Reagan limit increases not quite linearly at very low temperatures, but then increases linearly at higher temperatures. If you blow up this part, you see that it increases quadratically with temperature. So their focus actually was on this crossover from the T-square regime for the resistivity to T-linear regime, which crossover extends over a fairly wide range of temperatures. They showed, for instance, that in this regime, you do have well-defined quasi-particles. For instance, if you ask for the quasi-particle residue, you find that it has a value 1, which is perfect. But then it decreases dramatically to become very, very small. Now, this region they sort of identified with a crossover temperature. Then they plotted a graph which shows how for this particular model system, the various temperature regimes depend on the whole doping value, that is, which goes from very small to somewhat larger values. And they found that there is a bad metal regime at a higher temperature, a sort of metal with quasi-particle regime at very low temperatures, and there is a large crossover regime. They concentrated on the crossover and on the fact that the system has good quasi-particles at very low temperatures, and this they exhibited, for example, by calculating the spectral density of a single particle, which has this semicircular form at high temperatures, but which develops a sharp peak at lower temperatures, at low excitation energies, which is like it begins to be a good quasi-particle part to the excitation, single particle excitation. And this peak becomes more and more peaky as the temperature decreases. So their focus was mainly on how this happens. That is, how as you reduce the temperature, the resistivity is dominated by the quasi-particle part of the single particle spectral function, and they showed that this does happen. I'm going to look at the opposite limit, in which you are at very high temperatures. There is no question of being or there being a good quasi-particle, or okay, you don't expect that there is a good quasi-particle, and then ask for why the resistivity is linear in temperature. I'm going to talk about two microscopic approaches which are both incomplete. One of them is based on the eigenstates of the many-body Hamiltonian, unknown eigenstates of some many-body Hamiltonian, which have eigenvalues epsilon p. And I show that formally that in the limit of the thermal energy being larger than typical excitation energies of this many-body electron system, the resistivity is proportional to temperature with a coefficient which is given in terms of the eigenstates of this many-body Hamiltonian. The other calculation, which is also incomplete, is based on an explicit approximation. It's a dynamical model. So, I take a very simple dynamical model, the Hubbard model for electrons on a lattice, and make an approximation to the solutions of this model for strong correlation. And from that, I infer that the resistivity at high temperatures should again be linear in temperature with a coefficient A, for which I obtain an explicit expression in this dynamical model under a particular approximation. Both of these are actually based on the belief that the thermal energy is much larger than the excitation energies in this Fermi system. They are actually inspired by the fact that in pure metals, that is in coupled electron phonon systems, where the resistivity is due to the scattering of electrons by phonons, one does have linear resistivity above the quantum energy scale. Actually, see, in the phonon quantum energy scale is h/omega d, where omega d by is the d by frequency. So if the thermal energy is larger than this, they do show linear resistivity. As a matter of fact, they show linear resistivity for somewhat smaller thermal energies. Okay. So the first result which I am going to talk about is the exact eigenstates result, starting from the Kubo formula, which is the microscopic formula for the linear response of a system to an external electric field. So this is the conductivity in terms of that, in terms of let us say current fluctuations of the system. Now, if I write this term in terms of the exact eigenstates and the energies, this can be written as some matrix element square product of two matrix elements times some exponential factor and an exponential factor coming from the sort of Heisenberg time evolution of this current operator. Okay. Then if you integrate over the time in quotation marks, we take the q going to 0 limit and then take the omega going to 0 limit, you get the, and then take the high temperature limit in which the thermal energy is much larger than excitation energies, so that this exponential factor can be honestly written as this. Then one has the result that the DC conductivity can be written in this way in terms of the sum over the matrix elements of the Hamiltonian. Now, okay, I mean, what does it show? It shows that, well, conductivity can go as inverse of temperature, and so resistivity can go as a temperature. Of course, and this coefficient, well, it is shown here, but I haven't been able to calculate this coefficient. It is quite possible that there is a universal quantum limit to this coefficient for strong interactions, which could be due to electron-phonon interactions, electron-electron interactions, and so on. Okay. The other calculation is based on a particular dynamical model for the Hubbard model, which dynamical model which I developed with Deban and Sa long back again. This is a model for the orbitally non-degenerate Hubbard model. That is, you have electrons on the lattice sitting at lattice site I and j. At each site, let us say the energy is 0, and this is the energy due to hopping. And at a particular site, if I have one electron with upspin and another electron with downspin, they repel each other with an energy U. I ignore everything else. It's a highly oversimplified picture. Now, if you have this Hamiltonian, then the action will have a term like this, and this term can be written as a sum of two sort of self-interaction terms, a square of self-interaction terms, and this can be written as sigma dot omega, where the direction omega is a unit vector in some arbitrary direction. This is a well-known result for a spin half. Now you take this self-interaction term and do what is again well known called the Hubbard-Stacknovich transformation, in which a sort of, which is actually an operator generalization of the very simple result that exponential of x square can be written as this integral. The interesting feature of this is that here it is quadratic and here it is linear. So basically it converts the problem of electrons interacting with each other into a problem of electrons interacting, moving in some time-dependent potentials, which are the charge potential and the magnetic potential with the Gaussian weights coming from this factor. Okay. Now formally this is okay, I mean the direction of this is given by an SU2 matrix, the direction of this is given by a U1 term, which is the sort of phase of this is a spin-on, this couples to spin-ons, and so this is a kind of SU2 cross U1 lattice gauge field theory of coupled charges, spin-on fields, and the gauge Bose fields with Gaussian weight for their size. Okay, now nothing has happened, but now suppose you ignore the time dependence of the charge potential at each side, the magnetic field at each side, and this arbitrary angle. Then I call it stage 1. That is a classic. That describes electrons moving in the in a magnetic field directed randomly at static magnetic field directed randomly at each side, and a charge field which is also random at each side, and the weight of these is Gaussian. Then in stage 2, you begin to include the time dependence of these, and okay, there are ways of describing this in terms of some gauge fields and so on. Okay. Now, what I am going to talk about is just sticking to this stage. That is, in this stage, what you have is electrons moving in random static fields. This is the sort of high temperature limit. If you look at that, then you find that there is a spectral density. I mean, this problem also cannot be solved exactly, but it can be solved in the d equal to infinity limit, in which case the coherent potential approximation, or CPA, is exact. That is, the problem of an electron moving in a random potential can be solved exactly in d equal to infinity dimensions. And there is a fair amount of experience which says that those results are reasonably all right for 3 dimensions and so on and so forth. Okay. So in that case, when you can solve it exactly, and you find that you have a semicircular density of states, and there is a Mott-Hubbard gap. So this describes a system with, you see, this is the single particle density of state. It has no peak, so there are no quasi-particles. But because of strong correlations, there is a lower Hubbard band and an upper Hubbard band. All this is known in some form or the other, very well known in some form or the other. Okay. All right, so I use this model, which I believe is appropriate for a strongly correlated system at high temperatures to calculate some physical property, in this particular case, the DC conductivity. So the DC conductivity turns out to be some number, sigma naught, times the hopping integral T star squared times the derivative of the Fermi function times the square of the single particle density of states integrated over the frequency. Now, you see, it happens that again all these are in d equal to infinity. It so happens that in such in this d equal to infinity, in this infinite dimensional system, in calculating the response function via the Kubo formula, for instance, you can neglect what is called the vertex corrections. It is just a product of 2 single particle Green's functions, which are finally described by this single particle spectral density. The vertex corrections are of relative order 1 upon d, etc. I mean, this has been again done to death. Now, it turns out that this derivative, which is a symmetric function of the frequency, is of this form. It has a height of kT inverse at 0 temperature, a spread of about kT, and so it is crudely approximatable by something like this. You can approximate it like this, and the single particle spectral density has a it's a semicircular density of states with a width of about 2T star. I mean, minus 2T star here, plus 2T star here. This is single particle density of states. This is the chemical potential. And what you have in that inside the integral is the square of this, which is sort of even more sharp. So you find that as a result of this, the DC conductivity is proportional to beta and has this integral in it. This spectral density is non-zero only when this frequency difference is less than 2T star, is 0 above it. So the integration actually extends only to a length of T star, of the order of T star. So you find that the DC conductivity is inversely proportional to temperature and is proportional to T star. Okay, so this is one other calculation which gives you a similar conductivity and therefore a similar linear resistivity. So this microscopic calculation seems to suggest particularity of the linear coefficient. That is, the coefficient of the coefficient which is of the T in the linear dependence of resistivity on temperature. It depends on the material. But experiments seems to suggest the same scattering rate independence of scattering mechanism. This was actually shown in a very nice paper by Bruin, etc., in Science in March 2013. They took many systems. They plotted results for many systems, but one particular system in which they carefully looked at things was SR2RU2O7. That is another version of strontium ruthenate, in which at temperatures greater than maybe 100 or so, the thing seems to be an incoherent metal, and the resistivity seems to be linear in temperature. But well below that temperature, it becomes a coherent metal for which you can actually measure quantities like the Fermi or the Fermi energy, Fermi surface. You can find the effective mass and so on. And using those numbers, and using the, let us say, the Drude-like formula, they express the conductivity in terms of the scattering rate, and that scattering rate turns out to be linear in temperature. So that is one kind of experimental correlation which has been seen. They also found that resistivity of ordinary metals due to electron phonon scattering, which is also linear in temperature, is again follows this universal limit. So it's not very clear what is happening. Similarly, there is a paper last year which shows that the linear resistivity coefficient is proportional to the square of the London penetration depth, which also makes it somewhat non-universal. So at this point, I am quite confused. I do not know whether it is universal or not. I have made some attempts to understand this, and I hope this is a very interesting subject. Thank you.
I had a couple of simple questions. So, in your discussion of the first discussion, your first proposed explanation, you were using linear response theory. Is it known in the experimental regime that they're working in? Is that a valid approximation?
Yeah, very much so. Very much so.
Okay. And the second question was to make sure I understand something about the logic that I think I didn't get. You're relating you mentioned this limit. I forgot the name. The Mott something.
Yeah, the Mott-Jaffe-Regel limit.
Mott-Jaffe-Regel
right.
limit, and the metals are exceeding this by a lot.
Yes.
Is the idea that that limit is based on a quasi-particle discussion, and that's why
that's
why the absence of the quasi-particles is needed in order to exceed
That's
the limit.
the-
Is that the
that's
basic?
That's the party line, yes.
That's the party line, I
Right.
see. Okay, thanks. Are you in the party?
Yeah. If one talks specifically about the cuprates, then I think it's the correct statement that the linear resistivity, linear in temperature, occurs only at a particular value of doping, roughly speaking, optimal TC. And on either side of it is still a power law, but different. Does your approach shed any light on that?
No. I mean, it could be that the T-square region is very large on the overdoped side, but okay, I have nothing much to say.
Can I ask a stupid question? I mean, like, your talk of universe.
No, there are no stupid questions. There are only stupid answers.
Okay. So, actually, your mention of universality provoked me to ask this question. Your first approach which you mentioned, like, suggests me that the many-body interactions when you have will lead to randomization, at least in calculations.
Yeah, I mean,
and therefore, you should one should consider the statistical approach instead of, like when you were talking about the eigenvalue repulsion.
yes.
So those measures should be statistically calculated, right?
Well, these are when you are given a certain, you believe that there is a certain Hamiltonian which describes the system, you believe that it has some sort of real eigenvalues.
Well, I don't believe that there will be a single Hamiltonian describe your system. It will be an ensemble of Hamiltonian which will describe your system. That's what I mean.
It could be. I mean, generally, okay, I mean, most of these considerations begin with the assumption there is a single Hamiltonian.